Okay, we are back up and running for our final hour of math review. This is going to be hour 2 of math 3 and 4. For everyone that's been sticking with me since the very beginning, you guys all get kudos. I hope everyone has a fresh cup of coffee because we're on the home stretch here, going to knock out this last hour. For those of you just joining us, my name is Jadon Herron, and I am a civil engineer with Anderson and Perry and Associates. I've been with AP for just over 7 years now. Grew up here locally in Union and graduated from Oregon State University. Go Beavs. So with that, let's just go ahead and dive right back into our practice problems. We're going to wrap out this last hour working through a handful of practice problems here. So first one is number 11. Calculate the theoretical detention time in hours for the following water treatment plant. Our flow rate is 12.2 million gallons per day. We have 4 flocculation basins measuring 45 feet by 10 feet by 11 feet. We've got a sedimentation basin measuring 285 feet by 65 feet by 11.4 feet in average depth. 8 filters measuring 35 feet by 28 feet by 12.3 feet in depth. And a clear well averages 2.05 million gallons. So the first thing we want to do is we're going to want to calculate our overall volume. Because we've got million gallons per day, flow rate coming in. We've got volume of all our different treatment processes. And we want to calculate how long it takes for water to get all the way through this process in hours. So first of all, let's go ahead and calculate our volumes. So we have 4 flocculation basins. Each one of those are going to measure 45 feet by 10 feet by 11 feet. So 45 times 10 times 11, we get 4,950 cubic feet. We have 4 of these though, so that's going to equal 19,800 cubic feet. Now we have 1 sedimentation basin measuring 285 feet by 65 feet by 11.4 feet. So 285 times 65 times 11.4 is equal to 211,185 cubic feet. Now we have 8 filters that are measuring 35 by 28 by 12.3. So we have 35 feet by 28 feet by 12.3 feet. That's going to give us a total of 12,054 cubic feet. But we're going to have 8 of those, so let's multiply that by 8. That gets us 96,432 feet cubed. Okay, now we're running into a little bit of a hiccup because our clear well is averaging 2.05 million gallons. So we have our storages in cubic feet, and now we have one in million gallons. We have a flow rate though in million gallons per day. So let's go ahead and convert our total storage that we just calculated in cubic feet into million gallons. So we sum up each one of these. We have 19,800 cubic feet plus 211,185 cubic feet plus 96,432 cubic feet. And that's going to equal 327,417 cubic feet. So now we need to go ahead and convert our cubic feet into million gallons. And let's see what we have over here. 1 cubic foot of water is equal to 7.48 gallons. So we have 1 cubic foot is equal to 7.48 gallons. So cubic feet are going to cancel cubic feet. We get 327,417 times 7.48. I'm just going to go ahead and divide this by 1 million in order to get million gallons. And with that, I'm going to get 2.45 million gallons. Okay, so what we just did was we just summed up all of the areas, or all the volumes, excuse me, that we had in the 4 flocculation basins, the sedimentation basin, and the 8 filters. And that was a total of 2.45 million gallons. Now we also know that we have a clear well that averages 2.05 million gallons. So let's add those together. That gives us a 4.5 million gallons. So now we know we have a total storage of 4.5 million gallons. And we know that our flow rate coming in is 12.2 million gallons per day. But we're trying to solve for our retention time in hours. So we know that in 1 day, there's 24 hours. So million gallons cancels million gallons. Days cancel days. We end up with 4.5 divided by 12 times 24, which is equal to 9 hours. And this is what we get when we get in a hurry. We see that I have an answer of 9 hours, but we go over and we look, and we don't see anything that has 9 hours. Let's step back and look. Luckily, we wrote everything out. So we know we had 4.5 million gallons of storage, 12 million gallons per day. But if we go back and read the problem, we actually see we had a flow rate of 12.2 million gallons per day. So let's run this through one more time and do it correctly. So we know we had 4.5 million gallons, but our flow rate was actually 12.2 million gallons per day. And we had 24 hours per day. And this is going to equal 8.85 hours. So this is a good example why you always write everything out, track your units, and then you can double check your answer, make sure that you're getting the correct answer here. So the answer is going to be D, 8.85 hours. Okay, let's jump to problem number 15. Problem number 15. What is the flow through a membrane unit in gallons per day per square foot if the water flux of the unit is 4.75 times 10 to the minus fourth grams per centimeter squared per second? So this one's going to look a little bit overwhelming, but we're just going to go slow. We're going to track our units, and hopefully this is all going to make sense. So first off, let's start by writing out what we know. We know we have 4.75 times 10 to the minus fourth grams per centimeter squared per second. So what is the flow through a membrane in gallons per day per square foot if the water flux of the unit is? So water flux of the unit, what we're talking about there is it's a mass. So we have grams is a mass of water per centimeter squared is going to be per an area of the membrane, and then per second is just going to be a time factor. So what we're talking about with the flux is a mass of water per the area over a given time. So a weight or mass, an area, and a time. Now if we look at the units they want us to solve for, it's going to be gallons per day per square foot. So that's going to be gallons per day per square foot. So here we have a volume of water, a time, and an area. So we can convert seconds and days. That's easy. This is just a straight area, centimeter squared and square feet. We can convert that. Here we have a mass, but we know the weight of water, so we can convert from grams to gallons as well. Now the last thing here that's a little bit confusing is going to be how we wrote this out. 4.75 times 10 to the minus fourth. And what this is it's considered scientific notation. So another way we can write this is 0.000475. So these two are actually equal. And one way you can look at this is when we have 4.75 times 10 to the minus fourth, all we're going to be doing is moving this decimal point over 4 places. So that's going to be 1, 2, 3, 4. So that's going to be 4.75 times 10 to the minus fourth. Now we're moving it to the right because it was to the negative fourth. And if this was to the fourth, we'd be moving the decimal place the other direction. So let's just look at that real quick. Let's just say, for example, it was 4.75 times 10 to the fourth. We would take the decimal place 4.75, move it 4 places to the right. 1, 2, 3, 4. So then that would actually be 47,500. That's the scientific notation. But I digress. So let's get back on track here. So what we know is we have 4.75 times 10 to the minus fourth grams per centimeter squared per second. So let's go ahead and write this out a little bit differently so it makes a little more sense as we're tracking our units here. So we already talked about our scientific notation. So let's just go ahead and write this out as a decimal. So we know we're going to have 0.000475 and it's going to be grams. Now, it's grams per centimeter squared per second. So the way I wrote this out, grams per centimeter squared per second, this is equal to what they wrote over here. Grams per centimeter squared per second. This is just going to allow us to track our units a little bit longer. Now this is going to be a really, really long equation. So what I'm going to do is I'm just going to keep multiplying as we're converting. I'm going to track it over to the right. I'm going to drop down and just keep tracking it over to the right. It's all going to be one equation though. All right, so let's start converting. And this is where it's really important to track our units. So first thing I want to do is let's go ahead and convert the grams into kilograms. So that's going to be a straightforward conversion. We know that there are 1,000 grams in 1 kilogram. Now the reason I'm doing this is I'm going to now convert from pounds to kilogram. So if we come back over here and let's look at our conversions. 1 pound, here we go. We got 1 pound is equal to 0.454 kilograms. So we got 1 pound is equal to 0.454 kilograms. Okay, so we've gone from, let's write this as grams. So grams canceled grams, kilograms canceled kilograms. So right now we've converted this. If we were to run this math out, we would have pounds per centimeter squared per second. But we're trying to find our answer in gallons per day. So now let's go ahead and convert our pounds into gallons. So if we come back over to our cheat sheet, let's look at pounds. Okay, we know right here we got 1 gallon is equal to 8.34 pounds of water. So we're going to put the 8.34 on bottom. So we got 1 gallon is equal to 8.34 pounds. And again, this is where it's going to get a little confusing just because I'm tracking this around, running out of room. In reality, if you had a piece of scratch paper, it'd be a lot cleaner if you could just continue this equation all the way across. But for our purposes, it's going to come across and just wrap back down, come on the bottom here. So now we have pounds are going to cancel pounds. So now our units are going to be in gallons. So based on these conversions so far, we have gallons per centimeter squared per second. So now let's go ahead and convert our area. So we just converted from grams of water into gallons. So now let's convert from centimeters squared. Ultimately, we're trying to get it into square feet. So first thing let's do is let's convert from centimeters squared to inches squared. So if we come back over to our cheat sheet, we know that in 1 inch, there is 2.54 centimeters. But we have centimeters squared. So we're going to go with 2.54 centimeters per inch. But we have centimeters squared, so we're going to square this. So we have 2.54 centimeters squared per inches squared. But we're trying to get to square feet, so let's go ahead and convert from inches squared into square feet. So we know that in 12 inches, there's 1 foot. But this has to be 12 inches squared to get us into square feet. So now if we track our units, we're going to have centimeters squared are going to cancel centimeters squared. Inches squared are going to cancel inches squared. So now our last unit we have to worry about is our seconds. So we're trying to find trying to find our answer in gallons per day per square foot. So now we got to get from seconds into days. So I'm going to continue this on down here. We know that in 60 seconds, there's 1 minute. And in 60 minutes, there's 1 hour. And in 24 hours, there is 1 day. So seconds on bottom is going to cancel our seconds. Minutes cancel minutes. Hours cancel hours. So what we're going to be left with here when we're all said and done is going to be gallons per square foot per day. So this is going to be gallons per square foot per day. If we come back to our equation, that's gallons per day per square foot. All of our units are matching. So now this is going to be just an operation of running your calculator correctly. So for all of you that are following along, this would be a good opportunity to go through and complete this along with me. That way we know we're getting the right answer and we know we're running our calculators correctly. So we're going to start with 0.000475. We're going to divide that by 1,000. We're going to divide that by 0.454. We're going to divide that by 8.34. Now we want to multiply by 2.54 squared. Multiply that by 12 squared times 60 times 60 times 24. When we're all said and done, if we entered everything correctly in our calculator, we should be getting 10.07. And that's going to be gallons per day per square foot. If we come back over here, we round up 10.07, and we're going to get an answer of 10.1 gallons per day per square foot. So let's do a little recap here. The question originally asked, what is the flow through a membrane unit in gallons per day per square foot? The water flux of the unit is 4.75 times 10 to the minus fourth grams per centimeter squared per second. So when we first look at that, it's going to be very intimidating. All we have to do is write out our units, track our units, look at what conversions we know, and start converting. So we started by writing out 0.00475 grams per centimeter squared per second, converted from grams to kilograms, then from kilograms to pounds, pounds to gallons. Then we looked at our area, so we converted from centimeters, or from centimeters squared to inches squared, from inches squared to feet squared. Then we had seconds, trying to get to days, so we went from 60 seconds in a minute, 60 minutes in an hour, 24 hours in a day. All of our units tracked through, and we were left with gallons per day per square foot. And if we ran our calculators correctly, we should get 10.07 gallons per day per square foot. All right, let's take a look at problem number 18. A lime tank is conical at the bottom and cylindrical at the top. If the diameter of the cylinder is 15 feet with a depth of 28 feet and the cone depth is 12 feet, what is the volume of the tank in cubic feet? Give answer to 3 significant figures. Okay, So what we know here is we've got a tank that is conical at the bottom and cylindrical at the top. Let's just go ahead and draw this. So we have our tank. The diameter of the tank is 15 feet. The depth is 28 where the cylinder is, and 12 feet where the cone is. What is the volume of our tank? So let's just split this into two different tanks and calculate the volumes individually. So the first one we're going to have is going to be the volume of a cylinder. If we look at our cheat sheet, the volume of our cylinder is equal to 0.785 diameter squared times our height. So again, volume of a cylinder essentially is just going to be the area of the circle times the height. So this is equal to 0.785 diameter squared, which is 15, times our height, which was 28. And this is going to equal 4,945.5 feet cubed. So now let's look at and see what our volume of our cone is. So volume of a cone. Here we go on our cheat sheet. We've got 1/3 0.785 diameter squared times height. So as you notice this, all of this volume is it's just 1/3 the volume of a cylinder. So let's run through this. This volume is going to be equal to 1/3 times 0.785 times our diameter squared times our height. Run this through our calculator. And we get 706.5 feet cubed. We add these two together. We get 5,652 feet cubed. However, they asked us just to provide three significant figures. So what we're going to do is we're going to round to the three figures. So we're essentially going to drop off this 2. We get 5,650 feet cubed. Answer C. So recap this. Big thing is we can draw a sketch to make sure we fully understand what they're talking about. This is always useful. And then we had two different geometries. We had a cylinder and we had a cone. So we calculated the volume of the cylinder, we calculated the volume of the cone, and we added the two together. Okay, let's take a look at problem number 19. A watershed 158 square miles receives an average of 22.6 inches of rain each year. The amount of rain collected for treatment is 6.75%. How many million gallons of water are available per year for the small community that resides there? Okay, let's just draw a sketch again. So we know we've got some watershed. I'm just going to conceptualize this by drawing a box. And the area here is 158 square miles. Now, it receives an average of 22.6 inches of rain each year. So now, this is essentially going to be a box that's 158 square miles in area. And if we look at it in section view, our height of this box is going to be 22.6 inches. So first thing I want to do is let's calculate the volume of this box. That's 158 square miles, and it has a height of 22.6. This is going back to our concept of like the volume of a cylinder or the volume of a cube. You take the area of that and you multiply it by your height, and that's going to give you your volume. Now, this is just going to be another practice of tracking units because we have miles squared and inches. And we're trying to get to million gallons. So let's start by putting everything into feet. So we got 158 miles squared. Let's look at our cheat sheet, and what do we have here? Well, we know that in 1 mile, there's 5,280 feet. So let's start there. So we got in 1 mile, there's 5,280 feet. But again, we have to be squared because we're in square miles. So let's square the bottom to get square miles and square the top to get square feet. So our area is going to be 158 times 5,280 squared. It's a big number. We get 4404787 feet squared. Now let's take this answer here and let's multiply it by our height. So we have our area in square feet. Multiply that by our height, which was 22.6 inches. But we know there are 12 inches in a foot. So multiply that answer by 22.6. And we end up getting 9.95. Oh, excuse me. Got ahead of myself here. Let's try this one more time. So we take that answer, we multiply it by 22.6, and then we divide it by 12 to get us into cubic feet. And that's going to give us 8295682560 cubic feet. So that's how much water is over the entire watershed every year. So now let's convert this into million gallons. So we know that one cubic foot of water is 7.48 gallons. So we're going to multiply by 1 foot cubed divided by 7.48 gallons. Nope. See, we got that backwards. We'd be feet cubed times feet cubed. So we would have feet to the 6 divided by gallons. That doesn't do us any good. We're running out of room here, so let's go to a new sheet so we can write this out a little more clear. So we know we have 8 295682560 feet cubed. Now we know that in 1 cubic foot, we actually have 7.48 gallons. Now when we do the math, feet cubed are going to cancel feet cubed. Let's go ahead and convert this into million gallons so that in 1 gallon, in 1 million gallons, there is 1 million gallons. So gallons are going to cancel gallons. We're left with million gallons of water. So we take our cubic feet times by 7.48 and then divide by a million. And we get 62,051 million gallons. So what we've done at this point is we've taken 158 square mile area that had 22.6 inches of rain over that. We've calculated that volume in cubic feet. We took the cubic feet and we converted that cubic feet into million gallons. So we have 62,051 million gallons. However, going back to the original question, we know that the amount of rain collected is actually only 6.75%. So we're going to take our 62,000 million gallons. We're going to multiply that by our 6.75%, which in order to get the percent into a decimal, we just divide by 100. We take our 62 million gallons, or 62,000 million gallons, times that by 0.0675. We get 4,188 million gallons, which we're going to round up to be 4,190 million gallons. Okay, let's jump down and take a look at problem number 20. A softener unit has 118 cubic feet of resin with a capacity of 25.5 kilograms per cubic foot. How many gallons of water will the unit treat if the water contains 14.2 grains per gallon? So let's start off then with how much we can actually treat. So we know we have 118 cubic feet of resin with a capacity of 25.5 kilograms per cubic foot. So that's going to give us how much grains we can actually treat. So we've got 118 cubic feet of resin. And the capacity of that resin is 25.5 kilograms per cubic foot. Now we know that there are 1,000 grains in 1 kilogram. So kilograms cancel kilograms. Cubic feet cancel cubic feet. And we have grains. So that's how many grains we can actually treat with this resin. But we want to know how many gallons of water will the unit treat if the water contains 14.2 grains per gallon. So we know we have 14.2 grains per gallon. So now grains cancel grains. So we run our math through. 118 cubic feet times 25.5 kilograms per cubic foot. We convert to 1,000 grains per 1 kilogram. And we know that our water has 14.2 grains per gallon. This is going to equal 211,901 gallons. Which is equal to C, 211,900 gallons. So we started off with how much resin we had, 118 cubic feet, the capacity of that resin, kilograms per cubic feet. So that gives us a kilograms then, and we divided by our how many grains per gallon we had in our water in order to get our gallons, and just tracked our units through and converted as needed. Let's come down and take a look at problem number 21. A solution of lime needs to be prepared for a jar test. How many grams of quicklime, CaO, would you mix with 1 liter of water to make a 1% weight volume solution? So we want to know is how many grams of CaO do we mix with 1 liter of water for a 1% weight solution? So we know we have 1 liter of water, so let's start there. We know that in 1 liter of water, there's 1 kilogram. So we're converting our volume of water into a weight of water. We know that in 1 kilogram, there's 1,000 grams. So all we've done now is taken our 1 liter of water and converted it to grams. So we're looking for weight. Now we're looking for a 1% volume solution. We want 1%, which would be 1 over 100, or 0.01. Run our math through. Liters cancel liters, kilograms cancel kilograms, and we're left with grams. So 1,000 divided by 100 is equal to 10 grams of CaO, which is answer C. The next problem we're going to look at is going to be problem number 27. Problem number 27 says, which should be the chemical feeder setting in pounds per minute if 12.5 million gallons per day is treated with 7.25 milligrams per liter of soda ash. So let's take a look at our feed rate equations. So our feed rate equation, pounds per day, is equal to our dosage in milligrams per liter times our flow in million gallons per day times our conversion of 8.34 pounds per gallon. So let's go ahead and fill in what we know. We have 7.25 milligrams per liter, or also part per million. Our flow rate is equal to 12.5 million gallons per day times our 8.34 pounds per gallon. So we have million cancels million, gallons cancel gallons. This is going to give us a feed rate of pounds per day. Now we're assuming that we have 100% purity, so we're not going to divide by anything here. And this gives us an answer of 7.25 times 12.5 times 8.34, which is equal to 755 pounds per day. But we're looking for an answer in pounds per minute. So we know that in 1 day, there's 24 hours. And in 1 hour, there is 60 minutes. So we get days cancel days, hours cancel hours. And 755 divided by 24 divided by 60 is going to give us an answer of 0.5248 pounds per minute. We come back over and look at our problems. We can round up 0.5248 to 0.525, and the answer is B. All right, let's knock out one last problem today and we'll call her good. So we're going to jump on down to problem number 34. The level in a storage tank drops 4.25 feet in exactly 12 hours. If the tank has a diameter of 50 feet and the plant is producing 2.95 million gallons per day, what is the average discharge rate of the treated water discharge pumps in gallons per minute? So let's start by just drawing a little sketch here. So we got a tank, and this tank is a diameter of 50 feet. It's got some water level in it, and we know that it drops down exactly 4.25 feet in 12 hours. We have pumps that are pumping out of this to get that drawdown. But we also have inflow because the plant is producing 2.95 million gallons per day. So what is our outflow rate here in gallons per minute? So first thing is, let's go ahead and start with our million gallons per day. Because we got gallons per minute that we're trying to solve for, and we got million gallons per day coming in. So we know we have 2.95 million gallons per day times in 1 day, we got 24 hours, times in 1 hour, we got 60 minutes, times in 1 million gallons, we actually have 1 million gallons. So days cancel days, hours are going to cancel hours, million gallons cancel million gallons, we're left with gallons per minute. So we got 2.95 divided by 24 divided by 60 times a million, and this flow rate is going to be 2,048.6 gallons per minute. So if we go back to our sketch, this 2.95 million gallons per day. Nope, let's go back to our sketch here. Our 2.95 million gallons per day is actually equal to 2,048 gallons per minute. So that's one part of it. But we also know over the course, and this is just a constant. This is a 2,048 gallons per minute constant rate. But on top of that, these pumps kick on, and we know we're going to draw down this tank by 4.25 feet. So what's the volume of that tank? What's our volume of water that we evacuated from that tank? So we know that our volume is equal to 0.785 times our diameter, which our diameter in this case was 50 feet squared, times the height. The height we cared about was that drawdown, which was 4.25 feet. This is going to give us a volume of 0.785 times 50 squared. That's 4.25. That's equal to 8,340 cubic feet. But we're caring about gallons, not cubic feet. So let's jump back over here and take a look. And we know that in 1 cubic feet of water, we got 7.48 gallons. So let's get this into gallons here. So times in 1 cubic foot, we've got 7.48 gallons. Cubic feet, cancel cubic feet. And we moved 62,387 gallons of water. Now we know that this happened over the course of 12 hours. So let's divide that by 12 hours. But we care about minutes, so that in 1 hour, there is 60 minutes. Because we moved 62,000 gallons of water over 12 hours. Then to get from hours to minutes, we divide by 60. So 62,000 divided by 12 divided by 60 gives us a flow rate out of that tank of 86.6 gallons per minute. So if we jump back to our sketch, we know that we had 2,048 gallons per minute coming into this thing from our drawdown. We had 86.6 gallons per minute on top of that. So if we had 2,048 gallons per minute plus our 86.6 gallons per minute, that gives us a total outflow of 2135 gallons per minute. And let's see if we did this right. 2135, we'll round that up to 2140, and that's D. So we evacuated a total of 2,140 gallons per minute. That was the discharge rate of our pumps. Well, everyone that stuck with me for all 5 hours, you guys deserve a gold star and kudos to you. Hopefully we were able to run through this in a way that made sense for you guys, tracking units, doing the conversions, doing our order of operations, making sure that we're consistent, and hopefully you guys learned something. And with that, I'm going to sign off.